All right, so I want to keep going exactly where Fabian finished the other day, or he mentioned, he showed a similar slide like this one, but he mentioned, well, we will deal with this step of extending the model to other sectors tomorrow. So that's exactly what I want to do today. The remaining or the other elements, doing a lot of downloading of necessary data, processing that data, building the electricity system model is what we covered yesterday. And after adding all the other sectors and solving, we'll go with summarizing and visualizing the results. So a little bit of motivation. Can I? Yes. So a little bit of motivation of why do we need to couple the electricity system with other sectors? Well, because there are many sectors which are being electrified. They add demand to the electricity system, but also could potentially add flexibilities. And my target for today is to give you an overview of what's happened or what could happen in PyPSA-Eur. So some of the sectors that are relevant to include are the transport sector, land transport, including electric vehicles, but also shipping and aviation. What do we do with the whole heating sector? How do we deal with centralized systems, including district heating systems or individual systems? But also, how do we deal with demands from the industrial sector and all the different subsectors within the industrial sector, production of steel, cement, aluminum, etc. And then we also, what we do is to have a detailed CO2 bookkeeping or accountability through the whole system, so that we have a nice representation of carbon capture, carbon utilization, carbon transport, and then storage or long-term sequestration. Together with this, we need all the infrastructure, all the networks that allow transporting other energy carriers besides electricity, and that could be hydrogen, that could be gas, that could be CO2. So I'll also briefly touch upon how to model or how these networks are modeling in PyPSA-Eur. You can see here a temporal representation through a year of the demand coming from different sectors. We'll go through all of them. You can see in blue the electricity demand. The dark line is kind of the average. And then the shadow on the back is the values every 3 hours. And you can see that's roughly constant through the year for the whole of Europe. And then when we plot on top of that, let's say, heating demand, you can see that there is this huge seasonality with, of course, higher heating demand in winter than in summer. And this is what is going to trigger the need to, how do we optimize the capacities to supply heating, right? And there's a lot of discussion about, or we see that heat pumps could cover a lot of the heating demand, but we'll need to optimize them. Or the question is, how do we combine heat pumps supplying most of the heating demand with other technologies covering the peaks, right? Because heat pumps are very expensive or capital intensive. How do we cover these peaks of heating demand? Is this through heat resistors, through gas boilers, all this kind of combination of technologies, right, and optimization. Okay, and then I will also cover a little bit how do we model demands for other carriers such as methane, hydrogen, biomass, etc. What you can see in this slide is a simplified representation of the relations, right? We aim to with this figure to provide an overview. Not exactly every link or every relation is included, but you can see that there are more cumbersome relations, right? If we look, for instance, as one of the elements, we can see that it's connected to many others, right? So the way that this figure tried to represent what PyPSA-Eur is doing is that you have first many different sources. We can get energy from wind and solar, hydro, biogas, from fossil gas, fossil oil, biomass. We even represent here the atmosphere because that's an energy source for heat pumps. Then there are elements that can store or transport the energy, convert it, and even change or convert from one energy carrier to the other one. And the idea is to be able to supply all the demands that we will include in the model. And my goal today is also to go through which of those demands are endogenous, that is optimized by the model, and which of them are exogenously set, which most of the time it means they are set by some values in the config file that can be modified. Yes?
What is the cooling demand?
I will get to that point. We will go through every single sector and a rough overview of what's going on. So I will defer your question to that point. Then what we know is that, or what we can see is that if I look at one component here, let's say methane, it can have different origin. So the model can use methane that has a fossil origin. It can also use methane that has been produced by upgrading biogas. And once the methane, or it can even produce methane synthetically by combining carbon dioxide that has been captured somehow with hydrogen. And once the methane is there, it can be used to produce heat in a gas boiler or in a combined heat and power plant. It can be used in the industry, or it can even be used to produce hydrogen via steam methane reforming, right? So this is just an example of many of the elements and carriers that are interconnected in PyPSA-Eur when we add the different sectors. All right, so this is now the snake make graph with all the different rules. I won't cover them because they are almost impossible to read. You have a high resolution version in this link. But what I want to mention is that we cover, let's say, this left side of the slide yesterday. This is where the electricity network is produced, where the renewable profiles are produced. And then all this right side of the slide is mostly downloading and processing a lot of data that is needed to represent the different sectors. So when all this data processing is done, the different sectors are added. And I think it's very difficult to read, but I think this is the prepared network that includes only the electricity sector, something that we used yesterday. All the data processing for the different sectors get added to the electricity network in a rule that is called prepared sector network. And then we have this built these large optimization problems now with the representation of all the different sectors. And then the logic is the same, right? We solve that network and we do other rules for plotting or visualization, right? So fundamentally, nothing is different from what we saw yesterday. It's just that we have many more data processing steps. And that's most of my presentation today is also about how we process all this data. And I didn't mention, but you're of course very welcome to stop me and ask questions at any time. All right, so one important aspect is that we want to keep the spatial resolution when representing energy demands from different sectors and different energy carriers, because we want to keep this spatial resolution, and when later we'll talk about how we model transportation, we want to make sure that the demand from different carriers, let's say hydrogen, methane, it's varying according to location, right? So here you have some maps representing this, for one example, representing this electricity, this demand from different carriers, the electricity demand we saw yesterday, how it can be produced. But we also have information on, this hydrogen demand that varies depending on the location in Europe. There is demand from oil-based products, including oil, methane. There's also demand for heat, and I will describe in a minute the difference between the heating demand associated to individual system or centralized system. And we also have demand from solid biomass, right? So I will now go into at least the rationale of each one of these demands, together with the technologies that can be used to supply them. But you can keep in mind that in every case, all of these demand calculations are spatially resolved. All right, so one thing, we have already mentioned this, but one thing that I, at least in some of the courses that I teach are useful for people using PyPSA, is that now we are stretching a little bit the usage of PyPSA components to represent things and transformations that are needed when coupling the different sectors. So to give you some examples, buses is a word that comes more for the power system engineering and typically represents, a node in an electrical network where things are connected. There is the same voltage or power. But here, or in PyPSA, it also represents a node we are imposing energy balance, where we are saying that everything that is connected to that node and is generating energy, and everything that is consuming, withdrawing energy from that bus needs to be balanced on the time resolution that we are choosing for our model. So that means that we're going to have buses that represents the heating demand and production in a certain region or node. Same with hydrogen, the same with methane. And actually, if we extend this, we can also use this concept to represent balances of elements that are not energy, not in megawatt hours, such as the CO2 that is, let's say, we want to keep the amount of CO2 that we are emitting and absorbing to the atmosphere. We also do that through a bus, right? We mentioned yesterday still, the idea is that we can use buses in a more general way to represent energy balances. The same happened with links, and I think Igor did a nice presentation with for instance, the conversion or representation of an electrolyzer using a link that converts electricity into hydrogen. Another example is to use a link to represent a heat pump that is withdrawing energy from the electricity bus and putting energy into the heating bus with a certain efficiency that will represent the conversion efficiency of a heat pump. Then we can also use more complex links, multi-links that has many inputs and outputs. And I think an intuitive example could be let's say we have a combined heat and power plant that is using biomass. So then this will be withdrawing biomass from the biomass bus, and it will be producing many outputs. It will be producing electricity and heat because it's a combined heat and power plant, but it will also be producing CO2 emissions if we corresponding to those assumed for the biomass. In the same way, we can use stores, which come from the traditional understanding of being something that can save energy at some time step and then discharge later. We can use them to represent things like an available potential. If it's a store that start being charged at a certain limit and you allow it to be discharged through your optimization, it's actually representing a certain potential. Or we can use it to relax the energy balance. I'm saying here an hourly, but depending on your time resolution, but we can use it to relax an hourly energy balance constraint and make it annual, right? If we add to a bus a store that is for free and is infinitely big, what we are actually doing is that imposing that the amount of energy that is demanded of hydrogen or whatever carrier needs to be produced. But now, because the store is there and its value is zero, what used to be an hourly constraint is now an annual constraint, right? So I'm just saying that, I'm just bringing this as an example also of how you could use, if you're thinking or modeling something with PyPSA, how you could use PyPSA components in a way to help you represent things, right? All what I'm saying, you can also do it by writing the mathematical description of your constraint using LinoPy. But some of these things are quick tricks to help you build models. And we use them in PyPSA-Eur to represent the other sectors. All right. So let's start now one sector at a time, trying to provide this overview. And let's start with the two sectors that are, let's say, easier to be electrified. Let's start with the electrification of the transport sector, right? we'll have, or we expect to have, a lot of electric vehicles. That will be the main strategy to reduce emission in the land transport sector. We know actually that the existing rail is already electrified. So what we could say is, or the way we model this in PyPSA-Eur is saying, well, based on the existing amount of cars, most of them internal combustion engine cars, we take those numbers from national statistics, and we assume all of them will be electric vehicles with a certain battery and a certain charging, and they will be connected to a certain charging capacity, and we represent them lumped, meaning we represent the behavior as all the cars in a certain region in the resolution that we are using in PyPSA-Eur, and the way they can interact with the power sector. So first, what would we need to represent electric vehicles? Well, we need some time series on when are they actually consuming electricity. So we get this time series from traffic counting data. This is part of the data gathering and processing. You can see here an example from any of the week. The statistics coming from Germany, and the blue is when are the cars being used. Then we can start with there are different options to be selected in the config file, but we can start with the easiest one, that is just assuming that the EVs get or needs to be charged right after being used. So then it's as simple as saying, well, there's a electricity demand coming from the EVs, different from a region, that is just displaced a little bit from the transport demand, will be this orange dotted curve. And this will be a very inflexible use of EVs, right? I came back home and then I charged the EV. But we know they can also provide a lot of flexibility, so we also allow in PyPSA-Eur that they can do demand-side management, or they have a battery that can be charged whenever it's more convenient for the system, and this is represented by adding a battery. As I said, it's represent a lumped battery, so it represents the energy capacity of all the EVs in a certain region, and that will be, and in the configuration file, you can select what percentage of all the electric vehicles in a country are allowing demand-side management, or they can be even a little more smarter, and they can also do vehicle to grid. They can discharge into the grid the batteries, and you can also say, well, I don't know, 50% of the cars are doing demand-side management, but also only 20% of them are doing vehicle to grid. And this means that the stores and links that represent the cars has a capacity proportional to this number of cars. Then we may think, well, but okay, even though the cars are smart, they are not always parked and charged, right? So there's also a time series representing availability of cars, or representing when are the cars connected to the grid, so they can do this smart charging and even discharging. And roughly speaking, cars are parked and connected when they are not driving, right? So this availability time series, you can see more or less is just the opposite of the driving time series, right? You can also say impose things, and one of the constraints that is imposed and described in the config file is, well, people own EVs to use them, and they want the EVs to be charged in the morning. So you can say, well, the filling level of the batteries, or the state of charge, needs to attain a certain level. I want them to be 75% charged at 7 a.m. because this is where people are going home. All these parameters and values that I'm mentioning are just default values, but all of them can be adapted, right? So this will be a representation of the electrification of transport that takes into account how this is impacting the operation of the power system. I want to say that this is what we call an exogenous demand. So the users select in the config file all what I described. And there is very close to be merged, I think, but we have, yeah, it's almost ready. The endogenous transformation of the land transport. That will be that the model decide, is it better to buy or to I want to say install, but is it better to have more EVs in the car, or to keep some internal combustion engine, or even to install or buy in the system more cars using fuel cells, so they have low efficiency, but they are using hydrogen. And the fact that this could be decided by the model based on a cost optimization is what we'll call an endogenous option, and will be soon available. But what is currently available is all what I describe on how we model exogenous. Yeah?
Do you consider electrified road and hydrogen transport?
So the electrified road transport, again, what is currently in the repository is that all the road transport, including passenger, light duty, and heavy duty, are all represented through EVs. But it's also very close to be merged. The splitting between passengers and light duty and heavy duty vehicles, both being either electric, based on hydrogen, so fuel cell cars, or heavy duty transport, and internal combustion engine. And when I say that they are different, I mean that they have different time series for how they are used, right? Heavy duty don't have this, they have different pattern, but also they have different cost per vehicle, different capacity of the batteries, different capacity of the charging. Yeah. Any other question regarding transport? Not then, yeah. So rail is mostly electrified. It's part of the electricity demand. But you could, there has been some discussion on using electric, I don't think anymore. There used to be some discussion on this hydrogen trains, so you could also allow that. But I think most of the, yeah, I think in Europe this is not a discussion anymore. We
know that the rail is used for quality.
Yeah.
When you say this coming soon, you mean PyPSA 1.2?
So PyPSA is the package that includes all the components, right? I think I don't want to say exactly soon, but it's there, right? It's so the 1.0 will be only for PyPSA, not for PyPSA-Eur. It's a pull request in the repository. What will be coming soon is the endogenous competition. All the other elements are there. All right. So then let me give you an example of the heating demand, because it's another nice example of a sector that could have a strong connection with the electricity, could have heavy electrification. So first thing that we need to discuss is how we model heating demand. And there are two components of the heating demand: space heating and demand for hot water. Space heating demand is based on a very classic approach of heating degree days and daily profiles. Heating degree days is just the heating demand is proportional to the ambient temperature, or to say correctly, to the difference between the ambient temperature and a threshold temperature below which there is heating demand. This is using the same input data, the same weather data that we use to produce a time series for wind and solar. So we assume consistency. And then it's weighted by population. So in every grid cell of the weather data that we have, depending on how many people are living there, what is the ambient temperature, and whether the ambient temperature is below, I think the threshold is something about 15, 16 degrees, then the heating demand is proportional to that. And then, of course, as with wind and solar, it's aggregated to the regions or to the nodes that we have selected in our clustering. This is what is happening for space heating, and this is what is driving the high seasonality of heating demand in Europe. Then there is also a constant water heating demand. And these two things are used to create the annual, or let's say the temporal profile, and then they are scaled based on statistics on historical annual demand. This is done automatically for two types of regions. regions where there are high population density, cities, where potentially district heating system can be developed or could be developed. And then regions that we call rural or regions with individual systems in which the population density is so low that a district heating won't make sense. And this is because the technologies that we can use to provide heating, if people are living in a urban area or in a region with district heating, are different to the technologies that you can use if people need to deal with individual systems, right? Cooling demand, current cooling demand, just for that, is included in the electricity demand because most of the cooling is electrified. But cooling demand can also be calculated based on cooling degree days using the same data set and added if you want to make assumptions such as because of temperature increase due to climate change or because of population getting richer and wanting to get more access to air conditioning, this is going to increase. But the current setup is there because it's part of the electricity demand of today. So with this, we kind of calculate the heating demand for these two regions, regions that can use district heating and regions that cannot. And then we include different technologies. And the competition or the selection between the different technologies is totally endogenous. It's decided by the model. If we start with the individual heating, so heating can be supplied by heat pumps, either air or ground source. We can use resistive heaters, any kind of boilers using gas, oil, hydrogen, solar thermal. And then it's also assumed that there are small thermal energy storage, water tanks, because they represent individual systems. They have a relatively high self-discharge, so they represent a typical situation in which you have a few hundred liters tank at home, but you can only use it to do buffering for a few hours, because if you have it more than a few days, it will cool down. On the other hand, all the demand that is associated to regions where district heating can be employed, they have the same heat pumps, the same technology heat pumps, but now they are centralized heat pumps. And this means that according to our technology data, they have a slightly higher efficiencies and a slightly lower cost per unit. There's also resistive heaters, all kind of boilers, but also combined heat and power plants that will be producing electricity and heating and can use as inputs gas, hydrogen, biomass. We also have solar thermal. We also have the waste heat from industrial processes that can be input into this energy balance, because this is representing a district heating. And here we have long duration hot water storage. So the difference is that this storage represents more a big water pit like the one in Høje-Taastrup you guys are working with and you might have heard of. So this represents a storage that is discharged much more slowly, so that you can actually do seasonal balancing. You can save some or charge some hot water during summer or whenever it's more convenient for the system, and then discharge in the winter. And we generally see this being used a lot to deal with the strong seasonality that I mentioned before. What else? Combined heat and power, you have the option to model the fact that they can be operated in a flexible way so that you can tune a little bit the amount of heat and power that you produce out of a combined heat and power plant. But you also have the option to represent a more standard operation in which they are operating the back pressure line, so the ratio between power production and heat production of a CHP is kind of constant. But if you want, and if this is important, there's also this operation. As I said, the selection between what capacity of these different technologies do I need in every node, it's totally endogenous, decided by the model. It can also, there's also a endogenous co-optimization of investing in building renovation to reduce heating demand. and how this can compete with, let's say, putting more money into investing in more capacities providing heat and more fuels to provide that heat. Right? So this is kind of the general description of the heating sector. To give you an idea of the overview, Alex? So to give you an idea of what's happening with the heating sector. Yeah, sorry, before we go there, one of the critical elements that we see in the heating sector is that heat pumps are heavily used and heavily selected. And this is a nice example of representing a technology such as heat pumps that have an coefficient of performance for heat pumps that actually depends on the ambient temperature. So instead of assuming a constant efficiency conversion from electricity to heating, we impose a coefficient of performance that depends on time that has been calculated based on the ambient temperature using the same weather input data that we were using for the heating demand, for the wind, solar, all of that, right? So you see here a summary of how the heat pumps coefficient of performance for heat pumps that are using the air as a source, or heat pumps that are using the ground as a source. And typically you like those because are less or better in winter. How this is changing through the year, but also across the whole Europe. And this is particularly relevant because coefficient of performance is very dependent on temperature and is low when ambient temperature is low. So it's when you really need them because there is a high heating demand. So it's important to capture these nuances that a heat pump dimension to be operated in the winter needs to take into account that there is a lower coefficient of performance during the winter. But it's also an example of something that if you think your technology efficiency depends on ambient conditions, you could also do that just by selecting a time-dependent efficiency. Yeah, I didn't mention geothermal heat because this has been integrated very recently, but there's also a possibility to model them in the heating sector. And what I wanted to get to is this, again, Europe overview of what is happening during the whole year. So what I said is that the capacities are endogenously selected by the model, and then also, of course, the operation. So you see this energy balance. This is aggregated for the whole Europe, but you could get one of these for every single node that you are modeling. On top, how heat in this case is being produced. On the bottom, how heat is being consumed. How it is produced, you see a lot of green. So the idea is a lot of heat pumps. But then you also see some brownish element during the peaking periods. And if you look at the legend, they correspond to, let's say, both. In centralized system, you mostly see operation of gas combined heat and power. In individual system, you see a lot of boiler, typically. But you also see that the other brownish element here is this discharging of centralized thermal energy storage, these water pits that we were discussing before, that tends to charge during the summer. That's where you see them as consumption on the bottom part, and then discharge during the winter to do this balancing. You can see more things, right? You can see this purple, which is the excess heat from electrolyzers that are being dumped and used in regions where district heating systems are allowed. And yeah, and some other small details. I think, yeah, there should be also a little bit of heat coming from physiotropes, the production of synthetic fuels. But the idea is that you get this kind of information for every single node that you're modeling, and you can understand the temporal balance. Right. So this is, yeah.
How about the industrial heating demand?
So I will get to the industry in a minute, and how the industry demand is modeled. But just, yeah, so allow me to get to that. Right, so this is purely optimized by the model. So you have the heating demand. Here is something that is calculated based on the available data, right? So you have ambient temperature and population density and a certain assumption on a threshold temperature. When temperature drops below 15 degrees, I assume that there is heating demand. So you can calculate time series like this one. This is representative for Europe, but you actually calculate a similar time series for every node that you are modeling, right? So you have this kind of information. This is done in the previous kind of somewhere around here, one of these rules. And this is an input to the model. And then once you have the heating demand that needs to be supplied, the system co-optimizes in the same fashion as it does for the electricity generation, which capacities of technologies providing heat are optimal to minimize the system cost. This is co-optimized together with electricity in order to supply that demand. And this can include pure generators, such as I take gas and produce heat in a gas boiler, or it can include converters, such as heat pumps, that takes electricity, so it will add an endogenous electricity demand to the electricity bus and create heat. Or it can include storage that moves the demand from one time step to the other. And all these technologies are co-optimized in the same way as you decide, or as the model co-optimizes how much capacity for wind, solar, and gas backup you need. Make sense? Cool. Yes. Yes. I would say yes, but it's still, for me, it's like you have another dimension. You have decided before on how many temporal steps you want to have, what is the temporal resolution you want to have. You also decided on what is the spatial resolution, and now you have the dimension of sectors and technologies representative or important to represent the different sectors. Yeah? Cool. All right, let's cover a little bit the industry, and then we can talk about industrial heat and heat waste. Before we go to the industry, I want to briefly mention that some of the carriers or energy elements that are used in PyPSA-Eur are carbonaceous fuels that they used to be fossil. We have been using fossil methane and fossil oil for many years. But now they can be, and fossil methanol, but now they can be also produced synthetically. So before going into mentioning them through the different sectors, I just want to use this slide to say that you can always produce methane by combining CO2 and hydrogen. You can produce synthetic naphtha or synthetic kerosene by combining hydrogen and CO2. And you can produce methanol by combining CO2 and hydrogen. And every time that you do this, you need to take into account, you need to carefully account for the efficiency in energy terms of this conversion. So how much energy are you using to produce the new fuels? But you also need to take into account the amount of hydrogen and CO2 that you need to produce a certain amount of methanol, methane, or oil. By oil, I mean here naphtha or kerosene. So this is done internally by making sure that every multi-link that represents one of these components has the information on every part of the links that captures this, right? The amount of CO2 that you need per every megawatt hour of methane that you produce. And the decisions on whether you use or the model use, I will go into detail for the different sectors, but most of them, when you need to satisfy a certain amount of methane, it's endogenously decide whether if this methane has a fossil origin or has been produced synthetically. And the cost competition is there, right? Producing methane synthetically will be much more expensive, but because it will be using a CO2 that has been captured somewhere, it could be carbon neutral compared to a fossil methane that will emit CO2, right? And all this, I just want to emphasize with this example that this is what we mean, or one of the things that we mean by detailed carbon balancing accounting through the model. And all the efficiencies are read from the same database that we have been presented before. Yes?
Are you considering water as a carrier or as
Yeah.
an input or an output gas?
Not at the moment. Yeah, could be, but this is not. No.
On the CO2, now if you're having carbon sequestration and all that, so in PyPSA, are you monitoring the CO2 carrier, or are you doing the accounting separately if you put in a global constraint and CO2?
I will get to that point, but just to give you some intuition, if we put a global constraint on the CO2, we have, and this is a high level of abstraction, we have a bus that we call atmosphere that is just doing this accounting, right? Of all the generators, of all the elements that could emit CO2, every time that they do, there is a link that connects to that bus, and it's just a way of bookkeeping the CO2 being emitted. And every time that there is a technology that can capture CO2, I will get to that later, but let's say like a capture or a point source from a process emission in an industry, that's also including the bookkeeping. So then you impose that on an annual level, if you want to be carbon neutral, this needs to be equal. You can allow to emit a certain amount, or you can even ask the system to be carbon negative if you set up the constraint to be negative. Okay, so we will get there, but I wanted to use this as an example of things that are important to consider. Let's talk a little bit about industry. And before going into industrial sectors, it's relevant, I think, to mention that we have also detailed information on where are the different industries in Europe today. You can see here in the map, this is coming from another project, Hot Maps, that then the information is integrated. You can see all the big industrial production facilities in Europe. They are color-coded by the type of industry, and the size is how much they are emitting today. So if you look at Denmark, for instance, you can see this blue dot that represents this cement Portland factory in Aalborg. And equivalent you can see all in the different countries. And this Hot Maps database was kind of enhanced with data on ammonia plants. And the reason why it's relevant to have this information geolocated is because if we assume that there will be any transformation in one industrial sector, this could trigger new demands for some energy carriers that could impact the need for infrastructure, right? Example that I think was mentioned also before. Let's say we have the production of iron and steel, which is here represented in red. If those factories decided to, instead of reduce the iron using carbon like they do today and then emit a lot of CO2, if they decide to start using direct reduced iron, which means you use hydrogen to do the reduction, so you don't emit CO2, that's cool, that's nice. We are reducing the emission of CO2 from the iron industry, but this will trigger a demand for hydrogen for those industries. And it's important to know that this demand will appear in the locations where we have today steel manufacturing. Assuming, and this is a strong assumption, that those steel manufacturing facilities will remain where they are located today, right? But for the time being, or until we reach to the end of this slide, this is the assumption that manufacturing facilities remain where they are today. Then what is happening to the different sectors is that currently there are exogenous assumptions on how each of these sectors is expected to be transformed. All of this that I'm going to briefly describe can be, again, selected in the configuration file. So we go to iron and steel. It is assumed that instead of using the primary route and use integrated steelworks that emits a lot of CO2, there is first an increment of the recycling. So we use more the secondary route, and what is not obtained through recycling is produced through direct reduced iron using hydrogen and electric arc furnaces. So effectively, this means that the same, let's say, tons of material, the same tons of steel are produced, but now they demand more hydrogen, or they demand hydrogen, and they demand, let's say, more hydrogen and also more electricity if more electric arc furnaces are used. So this kind of changes in the amount of energy, different types of energy that every sector is requiring are done at a European level, but then it's calculated for different locations what this will mean, right? Depending on the size of all these factories. And all these things that I mentioned, like how much is the recycling expected to increase, is selected through the config file. Sorry?
Like with steel. At what point do you start importing steel?
So I think that the latest analysis is also what Fabian did and was published last week or 2 weeks ago, where you can understand better that you can either import steel or import or use steel locally produced in Europe and see how this will change. But if you are producing steel in Europe, you are then not accounting for, I don't know if I understood your question, but you are accounting for the energy requirement to produce that steel. Yeah. Let's go to other sectors so that you get an overview. Let's say we want to produce aluminum, right? We are also doing aluminum today by transforming aluminum ore into alumina and then aluminum, but then we assume that this is going to be transformed, so most of the sector will be using, there's a strong assumption on increasing recycling, but then also using methane for processes in the production of aluminum that require high temperature. And again, this is also set exogenously. We go through the other sectors. For cement, there is a demand for solid biomass to attain the high temperature needed. For many of the other sectors, like ceramics and other industries, it is assumed that when possible, the processes are electrified. So there's an increase in electricity demand for these locations. And in some cases, if the heat that they require is a low temperature heat, they can get this heat from similar to district heating system. If it's a high temperature heat or high enthalpy heat, then it's assumed that it's produced by methane or solid biomass. And this is setting some exogenous demand for those carriers located where the industry is today. And now there's a big caveat because there is a lot of work at the moment on doing this competition endogenously so that the model can select if it's better to produce heat at for a certain industry based on one energy carrier or the other, but this is still not fully merged, so the option is all exogenous, but highly configurable, right? You can always go to the config file and say, well, I think this assumption on increasing recycling of steel is very optimistic, very pessimistic, and I'm gonna change it. Other elements that might be worth mentioning is to produce ammonia, we need hydrogen. So the ammonia sector introduced a demand for hydrogen. That's what is exogenous, but then it's decided by the model, it's endogenous, whether this hydrogen has been produced electrolytically, so that's green hydrogen, via steam methane reforming, so that's gray hydrogen. And yeah, you can use hydrogen that later will be used to produce ammonia. You can produce that via steam methane reforming or gray hydrogen, but that will have CO2 emissions that will contribute to your global constraint. Or you can use the same process, but capture that CO2 in what is called blue hydrogen. And then you will have low emissions. So you can see, clearly you can see here a competition of technologies that we have included because we have a relatively good understanding of the cost of these three options, right? Production of ammonia requires hydrogen, and then whether this has a fossil origin, fossil plus CO2 capture, or electrolytic, have three different costs and three different efficiencies, but also three different consequences in terms of the CO2 emissions and hence the contribution to the global CO2 emission constraint. Make sense? Plastics is also a very nice, interesting sector. The idea is that currently there are assumptions on how much naphtha you need to produce the plastic as they are produced today in Europe. There's also an exogenous assumption on the amount of recycling, and recently it has been included the option to produce plastics through what is called methanol to olefins. So you produce ethylene, propylene, and then longer plastic polypropylene, polyethylene, or things that later you're going to use to produce a lot of plastic, or methanol to aromatics that also, without going into details, produce a lot of plastic components, right? So the idea is that we now care about the industry not only in terms of the energy consumption, but also in terms of the feedstock consumption today are coming from fossil oil. Let me quickly mention the last two big components, and maybe we can start considering on making a break. Elements that are here, although formally they will belong to the transport sector, but they require today a lot of demand for fossil fuels, are shipping and aviation, right? Currently, for shipping, what it's considered is that it can be the demand for energy in the shipping industry can come from methanol oil, and this oil, as I mentioned, could have fossil origin or synthetic origin, or liquid hydrogen or LNG. This is exogenous, so you go to the config file and you assume which of the carriers will be used, or either if you want some percentages. And there's also work on endogenizing this that will be available. And for aviation, similar, right? So today we use, the default assumption is that kerosene is used. It can be produced from synthetically using the Fischer-Tropsch reaction or have a fossil origin. And it could be substituted with methanol, currently exogenous, but you can also, or in the future, will be able to represent this competition. The logic behind is that the logic behind all this development is that we, from the very beginning, start including competition for technologies whose costs were relatively known, right? And we are slowly getting to more competition or including endogenous competition or new technologies that we have more cost available, because it's also a little risky to have competition on things that are not very mature. I don't think you learn much from that. Right. Any question before? Let me see. Yeah, I think we take some question from here, and then I will save the infrastructure and networks discussion for right after the lunch. Any questions so far? Yeah. That's a very good point, because I want a little quick on that. So this is existing industries. And the exogenous assumption is that existing industries will remain where they are today and will produce the same amount of tons per product as they are producing today. This is what is currently available. There's also nice work going on allowing the relocation of the industry based on cost competition and doing things like, should we move the steel production to Southern Europe because you have access to cheap renewable electricity or renewable hydrogen instead of building the infrastructure to transport that hydrogen? That's a very valid question, I would say with a lot of social implication, but that's a valid question in which there are people working, but it's currently not an option by default in the repository. The option is the industry is there, where it is today. The transformation of that industry transform the demand for different energy carriers, and the energy system is co-optimized to produce those energy carriers to satisfy that demand. Make sense? Yeah. So for things, I mean, for wind and solar, because this has a higher land impact, their potentials are calculated based on land availability, right? But it's done at a node level. So you say, in this node representing Southern Zealand, for instance, based on the land availability, I calculate that this, and then based on certain occupation and capacity density, I calculate this space to build so many megawatts of wind and so many megawatts of solar. But this is done, this is imposed, or this is used as a constraint for the maximum capacity of wind and solar that can be installed in that node. But then we don't go into saying, well, that capacity should be installed you know, in this particular location in Copenhagen or in northern Copenhagen or in southern Copenhagen. This is for wind and solar. And for the rest of elements, let's say wind, let's say if PyPSA-Eur fine, we need to install a gas power plant because it's needed to supply some resilience or whatever. We don't include information on when exactly within the node it will be installed, because we are not at that spatial resolution, but also because it's the assumption that the gas power plant is small compared to the size of the region that you are modeling. That's it. Huh? Okay, cool. Any other?
And to estimate the aviation demand, it is like just all the aviation is happening just inside Europe, or it is like also like it is going from Europe to US, so all these demands are also.
There is a lot of, I mean, on aviation demand, I think it's currently demand for aviation from Europe. Okay. Plus international, yeah, plus 50% of international, but not spatially resolved. So this demand of aviation in Europe that needs to be supplied. What I was gonna say, I was stopping to think if we include international or not, is that there's also a strong assumption that aviation is not gonna, well, you can select that in the config file if you assume that it's gonna increase, decrease, or not. All of these sectors could have demand reductions driven by many things. The one that is endogenously modeled is the heating demand. So this building retrofitting, where you could say I invest in improving the thermal insulation of my buildings, but things like I invest in convincing people of flying less are not.
So it is like the spatial resolution of aviation demand is like on the basis of airports, where like.
No. This is just demand for either kerosene or methanol. It's at a Europe level. So this amount of kerosene, this amount of oil needs to be produced within the European system to supply that demand. And yeah, one of the reasons is that after the break we will go into modeling the networks, but the idea with the network is the same idea with modeling, right? You want the model as simple as possible to keep what is relevant, right? And currently there are not many bottlenecks in oil transport, so it doesn't make sense to pay the computational penalty of modeling a network of oil if it's not acting as a network today. That's a little bit the rationale. You could do if you want, but it's always trying to balance or trying to use the computational capability to represent what is more needed or where there are more networks. All right.
What definition of green hydrogen do you work with in the model? Is it in line with the EU Delegated Act, or is it more like grid-based electricity?
Yeah, that's a very interesting question. And there are some nice work specifically on that by Igor, Lisa, and other people. I would say here there's no specific constraint on time condition or condition for certain periods. What needs to be fulfilled is that the hydrogen demand is supply, and that hydrogen is, so these two things, hydrogen demand needs to be supplied with any one of the three elements, and at the same time there's this global CO2 emission constraint. And the combination of these two things plus technological assumption on these things, for instance, if you're doing blue hydrogen, what is your capture rate? This kind of alter the merits between the two things, the three elements, and select them. Other than that, there is a specific work on imposing temporal balancing for calling things hydrogen and what that impact could have. Any other question? No? Yeah. You could have the solution that in one, I'm going to say it, but there's one location where there's a high hydrogen demand, but it's very far away from the main network. So it's and it's a very poor wind and solar resource. So it's very expensive to make it green, and it's very expensive to transport green hydrogen being produced far away. And then for that location, it's fine that it's cost effective to install or to keep using blue or even gray hydrogen. So this decision, this competition is taken at a spatially resolved level, but together with the rest of the network, right? It could be that you don't have a good wind and solar resource, but you have it far, and this together with building a pipeline, it's better than using gray hydrogen. And this global CO2 constraint is affecting this competition, but because it's a global CO2 constraint, capture all this, somehow connect. So the fact that there's a global constraint plus the fact that there are networks allowing you to produce energy carriers in different locations with better resource and moving them affects the optimal combination of capacities in different nodes. And you can do things like that. For instance, there is an option in which you allow or disallow the building of a hydrogen network. And you can learn what would be the implication of that.